In this video, we're going to discuss a very useful technique for solving differential equations. In terms of notation, we're going to let t denote our independent or dependent variable. Our independent variable or input variable. Typically, we think of t as representing time, and then our output or a dependent variable is y. So when we see a y, we need to remember that it's the same as y of t. Y is a function of t. When we see dy dt, we need to remember that that's the same as y prime of t. So a differential equation of the form dy dt equals f of y times g of t is said to be separable. What this means is that we can take dy dt and we can express it in such a way that the right-hand side is a function of y multiplied by a function of t. So let's take a look at some examples. Dy dt equals t over y. So again, the bottom could be written as y of t. We're just simply writing a y there. Now, can we write this as a function of y times a function of t? Sure. This is the same as 1 over y times t, so we could let our f of y be 1 over y and our g of t be t. So this is a separable differential equation. Another example. Dy dt equals 0.3y. Well, we could let our f of y be 0.3y, and there's no t here, but we could let g of t be 1. So this differential equation is separable. Of course, we could let f of y be y and let g of t be 0.3. That would work as well, but the important thing is that we can take the differential equation, the right-hand side, and express it as a function of y times a function of t. Dy dt equals 2y minus 3. The same idea. There's no t over here, no t term. Well, this is y of t, but we're not multiplying by any function of t. So I could let f of y be 2y minus 3 and g of t be 1. Now what about this example? In this example, I have dy dt equals t plus y. Now, because we're adding here, not multiplying, there is no way on earth that I can manipulate this so that I get a function of t times a function of y. There's no way I can manipulate to write in that form. So this is not a separable differential equation, and the technique we're going to discuss does not apply to this. So let's go back to the first one on the list. Dy dt equals t over y. This is separable. And let's prescribe that y of 0 is 2. And we're going to solve this using the method of separation of variables. So the big idea is that because we can rewrite the right-hand side as a function of y times a function of t, we can separate things and we can get all the y terms on one side of the equal sign and all the t terms on the other side. If I cross multiply here, I get y dy equals t times dt. So how do we get rid of the dy and the dt? Well, the simplest way is to compute the indefinite integral or anti-differentiate each side. So we get y dy, the integral of that, equals the integral of t dt. The antiderivatives, y squared over 2 equals t squared over 2 plus c. Now, these are indefinite integrals. So there really is a plus c here and a different plus c there, but we can sort of glump them together, that's the term I like to use, and write a single arbitrary constant on the the right-hand side. In other words, there's a c1 here and there's a c2 there, and we could sort of glump them together as c on the right-hand side. Now, we need to figure out what c is, and we're going to use the fact that y of 0 is 2 to do that. So if I substitute 0 in for t and 2 in for y into this expression, this equation, I would get 2 squared over 2 equals 0 squared over 2 plus c. So this goes away. This will be 4 over 2, which is 2, so that says that c has to be 2 in order to satisfy our differential equation and to pass through the point 0, 2. So that means that y squared over 2 equals t squared over 2 plus 2. If I multiply each side by 2, I get y squared equals t squared plus 4. Taking the square root of each side, I get y equals plus or minus the square root of the quantity t squared plus 4. Now, we can nail down whether we use the plus or minus there if we recall that y of 0 is 2. If we substitute 0 in for t, we'd get a 4 under the square root. And in order for the result to be a positive 2, we'd have to use the positive sign for the square root. So y of t ends up being the square root of t squared plus 4. And we could actually check that that's a solution by substituting that formula for y in to each side of our original differential equation. The next example, dy dt equals 0.3y. We said this was separable. Y of 0 is 0.5. So let's get all the y terms on one side and all the t terms on the other side. So I'm going to write this. I'm simply going to divide by y and then multiply each side by dt. So I have dy over y equals 0.3 dt. Now I could divide by the 0.3 as well, but then I'm dealing with 1 over 0.3, and you'll see in a few minutes that it's actually simpler just to leave it over here. Let's integrate each side. So the right side will be 0.3t plus an arbitrary constant, and the left side is going to be the natural log of really the absolute value of y, but we can write this as the natural log of y, and you'll see how that works out in just a moment. So don't really worry yourself with the absolute value here. So we have the natural log of y equals 0.3t plus a constant. Now again, there's an arbitrary constant on each side, but we just sort of clump them into one constant. Now we need to solve for y. So we exponentiate each side. So we take e to the natural log of y, that gives us y, and then we take e to the entire quantity between my fingers, which gives us this. Using properties of exponents, e to the 0.3t plus c, we can write that as e to the 0.3t times e to the c. Now c is a constant, e to the c is a constant as well, so we're just going to express this as a new c. So e to the c is a constant. We're just, for the sake of simplicity, we're going to write it as c itself. So we know that y equals c e to the 0.3t. Now to figure out c in this case, we're going to substitute our known fact that y of 0 is 5. If I substitute 0 in for t and 5 in for y, I get 5 equals c times e to the 0, which is 1. So that says that c is 5. So our final solution is y of t equals y, or y of t equals 5 e to the 0.3t. And this is the standard exponential growth. Let's do the next one on the list. dy dt equals 2y minus 3. We're going to assume that y of 0 is 3. We said this is separable. This is my f of y, and my g of t was equal to 1. So we're going to divide each side. We're going to divide by 2y minus 3 and multiply by dt. In other words, cross multiply. So we get dy over 2y minus 3 equals dt. We integrate each side. Now on the right side, we're going to have just the integral of dt. On the left side, we're going to have to do a simple u substitution. So the right side is going to be just t plus a constant. Let's take a closer look at the left side. On the left side, let's let u be 2y minus 3. So that means, after a little bit of algebra, that dy would be du over 2. So we could take this entire integral and express it as 1 over u times du over 2. So you might want to take a few minutes to actually fill in the details here. This 2 in the denominator comes out as a half. So we have 1/2 the natural log of u equals 1/2, and back substituting the natural log of 2y minus 3. So here's where we're at. 1/2 the natural log of 2y minus 3, which is this, equals t plus c. Now I should mention again that we don't really worry about the absolute values here because it all comes out in the end. Now we need to solve this for y. So the first thing to do is to multiply each side by 2 so that we isolate the logarithm. So we have the natural log of 2y minus 3 equals 2t plus c. Now c is a constant, so 2c is a constant. So we're going to call this our new c again. Our new c again. Now we have the natural log of 2y minus 3 equals 2t plus a constant. We're going to take e to each side so that we can get at that 2y minus 3. So we have 2y minus 3 equals e to the 2t plus c. And again, just like in the previous problem, we can write this as e to the 2t times e to the c. Now, e to the c is a constant. So just like in the previous problem, we're going to write e to the c as a constant, so I'll write it as the newer constant. Okay? The idea is that if you have an arbitrary constant floating around, like a c, 3c would be a constant, e to the c would be a constant, because in the end, we're going to use the initial condition to figure out what c is. So let's do that. We know that 2y minus 3 equals c e to the 2t. We know that y of 0 is 3. That was given at the beginning. So if I substitute into this equation 0 for t and 3 for y, I get 2 times 3 minus 3 equals c e to the 0, which is 1. So 6 minus 3 is c. In other words, c is 3. So that means that we have 2y minus 3 equals 3 e to the 2t. Now it's y that we want to solve for. So let's add 3 to each side, and then let's divide by 2. So here's our solution, 3/2 e to the 2t plus 3/2. We could check this by substituting into each side of our differential equation. Here are some problems for you to do using the separation of variables technique. dy dt equals t squared times y, or y of t, and y of 0 is 1. dy dt equals 1 minus 3y, y of 0 is equal to 1 there. So for each of these, the process will involve separating the variables to get all the y variables on one side, all the t variables on the other. Now remember that when I see y of t, it's really the same just as y, if you want to think of it that way. So you want to get all the y variables on one side, all the t variables on the other side, integrate, figure out any constants using the prescribed points, and then solve for y. So in the end, your answer should be y of t equals a formula in terms of t.